Hey there, folks. Let's continue on with our discussion. We've talked about a little bit of stuff that we're going to talk about eventually out of 5.2 when we talk about equivalence relations, and these are relations that have the properties symmetry, reflexive, and transitive. Those have those properties. But I want to move on to the kind of relations that I think we're probably most familiar with, and then ask that I'm going to ask you then to continue this notion of proofs and so forth, constructing proofs using the new definitions. Actually, the new definition for function is the old definition for function. So let's start with this. A function from, I'll call it f, for a function f from a to b, and I didn't mention that those are sets, but I think that kind of in the context makes sense, right? A function f from a to b, denoted f, and sometimes we'll use this handy dandy little notation here to indicate the first set, the set that we're coming from and the set we're going to, okay, is a relation. Now relations we've talked about. A to B such that it's all ordered pairs of the form A comma B such that is really I shouldn't say such that twice. Defined by, and then you've got all these points A, B that you would normally have in a relation, except B is a unique element of the set B. And what I mean by this is there is exactly one B for all A in the set A. Okay? That's different, right? We talked about that this morning, that in relation, that first set is just things that can be first coordinates. But what I'm saying now is, to be a function, everything in this set A, this first set, has to be assigned to exactly one element of P. Okay? For each A. So, and that's what I mean. It's not that you can't reuse the B's. You can. But for a particular A, it has to be a unique ordered pair. Okay? We use the notation. Let's continue with notation. And this is called function notation. I'm sure you're used to it. F of A equals B to denote A, B being an element of that function. Okay? Since we are using the entire set A in a function, we go ahead and call that set A the domain, right? Which that's exactly what we use. That's the same usage of the word when we're doing relations. It's just that it sometimes refers to a subset of A, right? Now it's going to refer to all of A. set A is called the domain of F, and the set B is called the, now range is the word that we tend to want to think here, but we're not guaranteeing that every element of B has something, that every element of B will appear as a second coordinate in these ordered pairs, right? I have no idea why it keeps doing that. Sorry. So we use the terminology codomain. Instead. Okay. Let's see if there's any other terminology that I want to throw into this. Domain I'm good with. Codomain I'm good with. There is one other word I could throw at you. If F of A equals B, we say that F maps A to B. You'll hear me say this occasionally. Or that B is the image of A under, I think that's a good, yeah, under F. Okay, so a little bit more terminology for you there. We use the notation F of, and we put a set here, okay. This is the set of all elements B in the set B such that F of A equals B. For all A in the set A. So in other words, it takes every element of A and maps it to a collection of things in B that are the images of the set A. In fact, we will call, this is a set that we would call the image of the set A. Okay? So when we start dealing with these things, remember, this is a set. Okay? And we know how to find sets, you know, how we know sets are equal, and how do we've done a lot of stuff with sets, how we show their subsets and things, right? So we know how to deal with sets. Just have to remember that this is a set. And we call this set the range of F. So there's that word again that we used with relations, and it's used exactly the same way. When we use the word range with relations, it means, okay, all the possible second coordinates of those ordered pairs. And that's what this is, right? These are all the possible second coordinates of these ordered pairs. Okay? The range will be a subset of the codomain. Okay? See if there's any notation, any. Okay, I think we're good. So we'll have you asking, you know, the question: is this a set? Is this, is this a function? These kind of things. There are a couple qualifiers that we can use on functions, special properties that some functions have. Okay, we that a function f from a to b is onto, or sometimes we'll say surjective. Yeah, right. Make sure I'm getting it right. If f of a equals b. Okay, so onto just simply means that everything in the set B is the image of something in the set A. Okay, one of the, if you want a kind of a cool example of an onto function, think about the function from the reals to the reals defined by f of x equals x cubed. Right? You think about what this looks like. Something like this, right? So for every value of y along the vertical axis here, we can find some value of x that gave us that y value, right? Just simply by taking the cube root of both sides. Okay, that won't work with x squared, right? If we're looking at x squared, that would not be onto the set of reals because all we get there are non-negative real numbers, right? The parabola opens upward, and we don't get any negative numbers that way. Okay? All right, so that's what we mean by onto. Another type of function that we could deal with, we say that a function f from a to b is 1 to 1, or injective, if having f of some value in a, I don't want to use b because then you'll think it's coming out of b. It's not. A1 and f of a sub 2, if this implies that A1 is equal to A2. Another way of thinking that is the contrapositive. I mean, you could say that if A1 is not equal to A2, then f of A1 is not equal to f of A2. But I'll be honest with you, that doesn't always help us. Having things not equal, there's all kinds of ways things can be not equal. There's only one way that things can be equal, and that is have the same value. So this is often a more useful way of thinking about it. And again, if you'd like an example, let's go back and look at our buddy f from the reals to the reals defined by f of x equals x cubed. Right? You think about this. If we were to take something, two different function values that were equal, they can only come from one place, right there. And so the only way those two y values, or horizontal values, can become equal is if we're using the same x values, right? Or the same first values. This kind of one-to-one, this is why we talk about one-to-one functions or injective functions obeying a horizontal line test, right? The vertical line test refers to the uniqueness of the B that goes with every A. The horizontal line test refers to the one-to-oneness of it, the fact that if you have one Y value, you have one X value. Okay, and that's where that one-to-one business comes from. Okay. And if you have both, the pen's kind of wearing out on me, I think. A function f from A to B that is both, I wrote it out like this, but you'll catch me doing this from time to time too, both one-to-one and onto that is called a one-to-one correspondence. Okay. Or and this makes sense, you got a surjection. Surjection means that everything, I should do it in the right order for you guys. Here's your B set, here's your A set. Surjection means everything here goes there. Injection means everything I've got right here will go to be injected into just one thing. I'm sorry, it goes the other way. Everything I've got here will be injected back into just the one thing right there. So put them together and you've got kind of things going both ways, right? So it's a bijection. Okay. I want to talk a little bit about the composition. Okay, we've dealt with composition before. Everything I'm saying here is holding the same standard as what we talked about before. I'm not changing any definitions. I'm just changing maybe the way that we think about them. Okay. If F goes from A to B and G goes from B to a set C, then G of F, okay, the G composed with F will go from A to C, is a function. We're going to have something. We have a starting point. You know, and because this is this set, we can kind of just follow it on through, because everything here has to be defined. Is a function defined by G of F. Okay, this is a set of ordered pairs A, C, such that F of A equals some B. I guess I should say there exists a B. There exists a B in B such that F of A equals B and G of B equals C. Okay. And then I left out for all A, but yeah, that kind of goes without saying. I said it was a function. Okay. So again, we will do a few proofs where we deal with the notion of some composed functions. Okay, I'm trying to make sure we get all our definitions in. That's about it. Okay. How do we, and if we talk about one-to-one, I think I mentioned this. How do you show something is one-to-one? Well, you look over here in this codomain, and you take a general element out of that, and you show that it maps back to something. I would really love to know why it's doing that. I'm very curious. Okay, sorry. Show that it maps back to something in that domain space set, right? To show that something is one-to-one, say take two values in the codomain set that are equal, okay, and they're the image of supposedly different things over here, and show that they have to actually be equal, the things over here, okay? So the homework will address things like that. In several of the examples, they actually define what the function is, and sometimes they'll just tell you it has a property, okay, and you'll have to draw upon those properties. So this is in 6.1, and I'm going to have you do problems 3, 5, and 6, and 9, and 11, and 12, and 13. Okay, so a few more problems there. Yet to come, and I'm going to start this as a separate lecture, the notion of inverse functions. We've talked a little bit about inverse relations, and now I want to talk about inverse functions. Okay, so I'll leave that alone and let you get to work on those problems. Remember that these are all things that we've pretty much dealt with. We've got some new concepts, one-to-one and on-to, but we've dealt with sets before. We've dealt with things. Just make sure you're keeping straight. Okay, here's my domain space. Here's my codomain space sets, right? And don't interweave them unless it's the same set, like R to R or something like that. Okay. I will leave you alone and let you get back to work on your homework. See ya. Let's see. Actually, what I want to do is exit full screen, and okay, I'm fumbling around, but I got it now.